yet to really exploit many of the technologies that could be used when you have multiple users sharing the channel, both in LTE as well as in Wi-Fi. So I think there's a lot of performance gains to be had there and technology to be developed. Some of my current work right now is looking at very large MIMO systems on the order of, 60 by 60 or more, primarily for higher frequencies like the millimeter waves. And the reason is that there's a lot of spectrum up at the millimeter waves, but to really be able to use it in a reliable and consistent way, you need a lot of antennas. And there's some very interesting things that our recent research has come up with in terms of being able to do non-coherent communication where you don't need to estimate the channel, even uncoded communication, taking advantage of the many dimensions as a form of coding. And so I think even though that technology is quite a ways out, I think it will enable a lot of the compelling vision for millimeter wave communication and also then back to the lower frequencies as well.
Okay. We're now up to, I see, 36 people. I see that we have Neil, who was the CTO of Alcatel, and before that was responsible for putting together most of the DSL networks in the United States. And a fellow who's been in the news lately, Steve Perlman, whose wireless system got a very enthusiastic write-up in the New York Times. He's using a lot of the tools here that have been developed by Paul and Andrea, in particular, like MU-MIMO, and is working on some interference things that may prove to be very interesting. Let's talk about what we're going to see in the future. Folks like Nokia think we're going to have 1,000 times the current performance. Is that realistic within, say, 5 or 10 years? Andrea first?
Sure. So I'm an optimist, and I do believe actually 1,000x is possible, maybe not in 5 to 10 years. And there's two places where I think we can get increased speeds leading up to 1,000x. I think in the next 5 to 10 years, we're looking at 10x and best case 100x. But longer term, I think 1,000x is possible. And the place where we're going to get those larger speeds, it is the following. I think at the physical layer, going to massive MIMO, which again only makes sense at the higher frequencies where you can have large antenna arrays. I think that's one place where we're going to get significant gains. I think, as I just mentioned, looking more deeply into multi-user
I'm going to interrupt you there because it sounds like there's a lot of feedback. Is your speaker fairly close to your microphone? And are they separate units?
Oh, let me mute my microphone when I'm, okay. Is this better?
Much better, and thank you.
Can you hear me now?
We've got Stanford professor Andrea Goldsmith, who's doing work on multi-user MIMO, and thinks it may just give us 1,000 times improvement over the next 10 years.
So I'll talk now. I've just muted my microphone. But the other place where I think there's a lot of potential gain for capacity increase is in far denser networks, going to small cells, not just in cellular, but also in Wi-Fi and millimeter wave. Basically, by decreasing the size of a cell, you can support a lot more users with that radio resource. But then there's other challenges that you introduce as a result. So even though that can lead to exponential capacity increase, there's other technical challenges in terms of deploying and managing and dynamically optimizing these small cells operating in a network with larger cells, particularly cellular. And also the backhaul is a big challenge as well.
Let's take that over to Paul. Paul, what kind of increase do you expect to see over 10 years?
We need to sort of differentiate between two things. One is the speed per user, and also speed that an AT can put out or aggregate speeds. It turns out that, so talking about speed per user, I think we looked at the last 10 years, we've been probably got a factor of 1,500 increase in throughput. Particularly Wi-Fi has done very well, and the LTE is not, cellular is not too far behind. So I would say, looking at the next 10 years, I think this trend will continue, and per user, I would bet on 50 to 100 increase in throughput. But a factor of 1,000 seems to be a little bit out. I would think that may be possible as the aggregate throughput at an AP level. I should explain that when you use massive MIMO in an AP, you're sending out multiple parallel streams to different users. So each user may not necessarily get an additional big increase in speed, but many users can share the multiple streams. And therefore, I think that a factor of 1,000 at an aggregate AP level, a factor of 50 to 100 at the user level seems within reach. No doubt there are lots of details, and the devil is the details.
Let me switch that over to Henry. You're doing a lot of work in advanced Wi-Fi now. I believe you were the first out there with 802.11ac. The problem to get these high speeds is when you have a lot of access points very close together, like the 42 or so that I could see right now in a Manhattan apartment building. Are the interference problems going to be solvable? What do we need to find out there?
I think
sure.
so.
I'm happy to speak to that. I think that the problem with the interference in Wi-Fi is something that you can't solve just within a single access point. The technology that we use for Wi-Fi multiple access today is not very sophisticated. In fact, it goes all the way back to the 1970s. And my new startup, Accelera, is actually looking at ways to manage interference across Wi-Fi access points from the cloud using software-defined wireless networks. And so the idea there is that you put software in the cloud that's dynamically managing Wi-Fi and doing a much better job at managing interference between the Wi-Fi access points than is possible with the Wi-Fi standard today. It's still standards-based. And I think that this notion of doing software-defined wireless networks for Wi-Fi goes across many networks as well. So if you look at cellular, the way that you would manage small cells in a large cell network could also use similar technology, and you could even see it transcend across other types of networks like cognitive radios or millimeter waves, where basically you have this software in the cloud that's dynamically managing the different wireless hardware resources and also handing off users and devices in the Internet of Things so that they're being supported by the network that's best suited to support that user, device, or application.
Let me interrupt here just to let people, I see a number of people are in an audio. If that was a problem that you couldn't get it on the video, it may be because I sent out a mistake, Marconi with a capital M, and you have to enter a password Marconi with a small m, and apologies for that mistake. Let's hand that over to Henry. You're actually working there every day trying to solve the problems with interference in Wi-Fi.
And I agree with Andrea's comments as far as the potential solutions, clearly coordinating the transmissions across access points so you can optimize power levels, and if you have enough MIMO capability, directionality of antennas and so forth, so that you customize the transmission per user. That's clearly the way to minimize interference and maximize throughput. But as she pointed out correctly, today's standards don't allow for a centralized controller like that across the access point. So it's a little more challenging in today's environment to deal with very large numbers of access points in small spaces. It's not impossible, but it's a much more challenging effort.
How long have people been working on this problem of putting control in the cloud in order to solve this access point interference problem? Andrea, how long have you been working on it?
So Accelera has been around for a couple of years now, and as far as I know, it's a relatively new space that kind of is taking advantage of the convergence of software-defined networking, which has really only come about in the last 5 years or so and gained a lot of acceptance in the wired network world. So some of those similar concepts are applicable here. And also the embrace of the cloud, which I think was viewed quite skeptically, especially by service providers and enterprises due to security issues and reliability and so forth. And now it's really become kind of mainstream. So I think the convergence of software-defined networking and wired networks and databases, as well as kind of the embrace of the cloud more broadly, has provided the opportunity so that I think now is the time. But as far as I know, it's a relatively new field, and I think our company is one of the first, if not the first, to be looking at this.
That's a company you founded, Accelera, I guess.
Accelera, that's right. So my first company was Quantenna, where we focused on hardware for Wi-Fi, and now we're looking at software to manage all the Wi-Fi access points. That's what Accelera's technology is focused on.
Now,
let me add a comment here. The question of interference in Wi-Fi, I think, is a serious problem. Actually, Henry touched upon it, and so did Andrea. And here I'd like to go back to what I was doing some 20 years ago. And in fact, I sort of chanced upon the idea of MIMO, worrying about interference cancellation. And in MIMO, what we really do is various forms of MIMO, single user, multi-user, cloud RAN, and network MIMO. We're really setting parallel streams to users, and they cross-interfere. And we managed to cancel interference by clever techniques. But in Wi-Fi, when it gets more and more crowded, we're going to see interference which comes uncoordinated from other APs, other PSSs. And so that's, unfortunately, the way Wi-Fi is designed, that these things run autonomously, and interference is sort of very fleeting and very disorganized. I do think that using antennas as a way of dealing with it is an important leverage. So there may be, we are doing many things today to improve interference across Wi-Fi networks. But I think an untapped dimension is antennas. More antennas, which now have to be much more intelligent to deal with fleeting sort of information that we get about what's going on elsewhere, and to try and cancel that interference or avoid interference. So to both Henry's and Andrea's remark, I would say more antennas is also a way of going at this problem, a very important problem.
So I'll second that or reiterate that statement. I think that, again, when we look at the multi-user MIMO techniques that I discussed a few minutes ago, the real benefit there is the more antennas that you have, the more spatial dimensions that you have, which allows you to separate out users without having them interfere with each other. So I think that's one of the huge advantages to multi-user MIMO in Wi-Fi as well as cellular systems.
Yeah, I've got to apologize. For some reason, we're not getting Andrea on the video, just on voice. It's enabled on this side, but WebEx is sometimes a little bit confusing, and it may not be recognizing the camera properly. We actually tested in advance, and it was working fine yesterday, so I'm not sure what was up. Question came in, and please send us more questions in the chat window. What are we going to see in the traditional definition of efficiency in wireless networks, spectral efficiency? That's now somewhere between 1.6 and 3.0, depending on how you measure it. If you measure it that way, what do you think we're going to see in 5 or 10 years? Paul, you're on screen.
Sure. Well, I think there are many leverages for spectral efficiency, and I would say that one way to do is to sort of go to higher level modulation speeds. And already in Wi-Fi, we are at 156 QAM. Now I hear rumors of we going to 1,000 QAM. So that means we get more bits per every hertz we transmit, and that's the way to go. It always comes at a price of getting higher SNRs and getting much better radios. So it's a climb, the mountain that's hard to climb. But I think we've begun to climb that mountain. We were 20 years ago at 4 QAM. We're now in production in 64 QAM, And we will, I think, in fact, probably in production on to 256 gram with Broadcom Wi-Fi chips, and probably go to 1,000 gram in a few years. But the other big way, of course, is getting parallel streams, MIMO. And with massive MIMO, you get, for example, you have 1,000 antennas at your AP, only possible in millimetric band, otherwise they get too big. You can really support 200, 300 users simultaneously. So your spectral efficiency will go through the roof, by a factor of 200 or 100. So with massive MIMO, if you can afford to have a large number of antennas at the AP, spectral efficiencies factor of 1 to 2 or 3 or 4 bits per hertz will look very small. You're going to see much higher numbers. So it's really exciting to go in that direction.
Now, what would that look like? It's hard for me to envision 1,000 antennae on a tower. What is it actually? What would it actually be if you wanted to have the 50 or 100 or even 1,000 antenna? How big?
So, of course, doing that in 1 gigahertz band today, for example, or 1 or 2 gigahertz band deployed in cellular seems a little difficult. There are people pushing for it also there. But already, for example, a cell tower may easily have up to 4 antennas per sector, 3 sectors, 12 antennas. Taking 12 to 36 might work out, but not much more, I think. But therefore, the key to number of antennas to go to higher frequency bands. Then the antennas become small. For example, at the millimetric bands, like say, let's say 24 gigahertz, the antennas, patch antenna will just be a 1 square centimeter. And it's pretty easy to put a panel at a base station, which is, let's say, a meter by meter panel with 1,000 antennas in that, or even more, a few thousands. So with high bands, these things are indeed possible. Of course, the question of price comes up, and the technology to make these things really cheap still needs some work, needs more work. But I think companies like Broadcom and Qualcomm and others are working on these, and I'm sure it will happen soon.
So the millimeter bands might be up at 28 gigahertz, even 60 gigahertz. How far can that signal go?
For me to jump back again, well, the answer is photons at 60 gigahertz or photons at 1 gigahertz fly exactly the same way. The 60 has an oxygen line. Let's go to 40 gigahertz. They're not too bothered too much by physics. The real problem is absorption by, absorption by rain, precipitation, and by foliage. And foliage is a problem. Even rain is not such a huge problem. The foliage is a problem, particularly wet foliage. And therefore, you got to find a deployment scenario that you don't have to go through too many trees. And one idea that I've been advocating is to put these millimetric band panels high up on a building, and you're looking down into a street with pedestrians, and you at the most go through one tree, mostly. And you pick up a 10 dB loss, but you got an enormous amount of array gain, focusing gain available at these antennas, because there are a large number of antennas. So you can easily burn through that foliage loss. So we need interesting deployment models to get over the foliage loss that you will have with millimetric bands. I do think that these things are solvable.
Henry, these guys are professors. They certainly have practical experience with companies, but they haven't built chips like you have. Do you think it's going to be possible to control that many antennas and build chips that will fit in the power and the space of putting one up on every block? So they got to be pretty small.
Sure, I think the antenna integration is not as challenging as Paulraj pointed out. You can, in a 1 square meter panel, you could easily fit hundreds of 40 gigahertz antennas. The issue, of course, is the electronics behind that, because for each antenna you need some signal processing, some RF, and some baseband signal processing. And that's, as time goes on, you can certainly integrate more and more onto these chips that we're building, certainly for the next decade or so. The Moore's Law will continue for a while. Power dissipation clearly becomes an issue as you do more and more of the signal processing in a small space. But, you know, when you're talking about a cell tower, you have a fair amount of space available. You have a fair amount of power available. So I certainly think it's technically feasible to get into the potentially hundreds of antennas on a cell tower as technology evolves over the next decade.
Hundreds, but not thousands.
Well, let's get to hundreds first, and then we can worry about thousands, one step at a time.
I saw one of our people who signed up is Antonio Ferenza, who used to work for Paulraj, I believe, in his earlier company. He, working with Steve Froman, has just done a demo of 8 access points doing this kind of cancellation there with a local server. I believe he used 2 PCs with 8-core Xenon processors to do that, to get those 8 working in real time, showing HD video. There's a really big jump from 2 PCs to chips you can put on top of every building and do 100 of them. What do you see as the time frame for that happening?
Is that for me?
I think you know a little bit more about chip making than our other panelists, not that they're unsophisticated.
Well, I think that you wouldn't scale that directly. You would actually change the architecture of the system. I think it's much easier for a demo to do it on a general purpose PC and just write the software to do all the signal processing. But ultimately, if you're going to deploy on a mass scale, you would do a custom chip with digital signal processors on it and whatever custom hardware you need, much like is done today in handsets and so forth. So you don't try to scale up the PC model, you scale a custom architecture. And that's how you can achieve going from a handful of processors to potentially processing hundreds of antennas with custom dedicated DSP hardware, and that is achievable.
Okay. People have been sending questions and keep sending them, and we'll get to them. But let me reintroduce our panelists. I'm moderating. I'm Dave Burstein. I'm just a geek. I'm not distinguished. You see on your screen Henry Samueli, who back around 1993 made some of the first DSL systems, went on to make some of the first cable modem systems, have created some of the most important Ethernet and Wi-Fi systems, and is now working on LTE and the future of LTE and other wireless that we're talking about. His company is WordCom, that he co-founded with Henry Nicholas back then. You've got AJ Paulraj, Stanford professor who invented MIMO, played a crucial role in WiMAX 4G, and much of what he did in the WiMAX 4G became crucial in the LTE 4G that wound up winning the business war there. And he's not stopping yet. He's talking about what is the future, call it 5G if you like. And his Stanford colleague, ANDREA GOLDSMITH, who's been working on cognitive radio, multi-user MIMO, the limits in theory of where you can go in wireless and many of these issues. It's an honor to be working with folks like that. Now, let's translate that into a picture if we can. I think I'm going to bring up Paul. We're talking about future networks. We know they're going to be more dense. They're going to have more antennas, more MIMO. They are probably going to be very close together in high frequencies. Why don't you describe what you think would be the network here in Manhattan, where I am, a high-density area that needs a heck of a lot of capacity when we look 5 or 10 years out? Will it be on every building in access point?
Thank you, Dave. I think that picture, I would agree, that picture is going to happen. And that picture brings up many issues, the architecture, the conductors, power, etc. But I think the big issue there, I think, will be interference. In cellular, there's a lot of native support within the system to try and deal with interference. There are a number of mechanisms called ICIC and others by which you can give up some degrees of freedom in time or frequency to try and coordinate across cells. Unfortunately, Wi-Fi had a very rowdy background. It grew up in a completely disorganized way, and Wi-Fi doesn't understand how to coordinate things together very well. So I think there's going to be a need to coordinate across APs in much more cleverer ways to deal with interference. And I also feel that antennas will be actually key to that. Antennas today in MIMO are actually really performing the job of dealing with interference, but self-created interference. And now the question is, it's interference across disorganized domains, and how do you deal with that? I think antennas is a very powerful tool, and I see the future where that will play a very big role. Just to go back to massive MIMO or multi-user MIMO that we all talked about, the traditional way of using massive multi-user MIMO is to have multiple antennas at one AP who are then talking to multiple clients simultaneously. We can also do this where you have these antennas distributed across a system, across a network, sometimes called network MIMO or network massive MIMO, network multi-user MIMO, where the antennas are distributed across in geography, and they are then coordinated to send beams to individual users. So there are many flavors that are coming up, and I think, for example, P-Cell, which is much in the news recently, is using some of these ideas. But I would say that to move forward in any of these things, to make it robust, it requires a lot of work. It requires the cooperation of many engineers in industry, in academia, in standards bodies, because and it needs the brain power of many, many people. So it's important that we all, as we see a wonderful future for wireless moving forward, we bring in brain power from all segments of society to work on it, because these problems are not easy to solve. It requires enormous amount of effort, and so my message is we have a huge future, but does require a global enterprise of research and development.
One of the questions that came in was, we're talking as though LTE is going to be dominant, but clearly Wi-Fi is going to be a major part of the future network. Do the same things apply to Wi-Fi? In particular, how do we deal with dense networks and interference? Paul, you're on, and then I'll give it to either of the other two who want to speak.
Sure. So interference is coming up. The bad news for interference in Wi-Fi is that in Wi-Fi, the individual, called BSS, a group of APs, a group of clients, do their own thing. They're not coordinated across APs, across BSS. Therefore, the patterns of interference are very random. It's hard to predict who is going to interfere with you at what time. You're unable in the standard to coordinate these things very well. So you have to think outside the box to find out ways to do this. And I believe certainly one can do things like power, and we can play some games with scheduling, a little bit of it, but not too much. But I think the real leverage is that antennas can deal with interference if they are set up correctly and given the right information. So I think the Wi-Fi future is enormous, but it's going to get increasingly hurt by interference. And I think we have to build standards and build ideas using more antennas to deal with interference.
The last Marconi webinar featured Marty Cooper. He won the Marconi Prize in 2012. Paul is this year's Marconi winner. Henry, I don't know particularly which year it was. Marty invented the cell phone, and he spent years working on beamforming antennas. They tell me they worked really well, and the problems were commercial and business. Are beamforming and intelligent antennas going to be crucial as we build the future networks? Paul, you're on screen, and I believe Andrea has some ideas on this.
Sure.
Henry?
No, Paul, go ahead.
Okay. Well, I think when Marty talks about beamforming, is really talking about MIMO. In MIMO, the way, for example, multi-user MIMO works, primarily how it works is that you're doing beamforming. To multiple clients on the downlink and beamforming on receive for multiple clients with uplink. And it turns out the early part of MIMO, for example, when MIMO first entered Wi-Fi and first entered certainly in WiMAX, beamforming was not done as a native to the system because for beamforming in transmission, you needed information on the channel and was a little hard to get. So the current standard support method of feedback mechanisms to get that information. So beamforming, that Marty talked about, really is beamforming in MIMO. And it is a center stage today in all our systems. Chip.com and all the others that use all have a beamforming in space.
Henry, I know that BirdCom has been active in the standards on this stuff. What kind of progress are we making now, and what are we going to have to move on to get the kinds of things we're talking about?
Well, it's steady. There's steady progress in all the standards between 3GPP and the Wi-Fi standards. It's a natural evolution in Wi-Fi. There are more bandwidth becoming available, higher levels of MIMO. In the 3GPP, as you move to LTE Advanced and eventually 5G, the standards are evolving to more MIMO capabilities that Paulraj talked about. So yes, it's just a slow, steady process, but it is moving forward because all the companies in the world have the same vision and they're collaborating. You may compete in the marketplace, but in the standards bodies, we all want to move the technology forward. So there is a good collaboration among most of the companies out there to evolve the standards to accommodate the massive MIMO technologies that Paul and Andrea were talking about.
Henry Samueli of BirdCom.
I can jump in as well. I think the point that Paul makes about beamforming being very powerful to mitigate interference is true, but it's not possible to take advantage of that today in Wi-Fi because the way that you mitigate interference between users with multiple antennas is basically coordinating the spatial dimensions they occupy. And unfortunately in Wi-Fi, the multiple access technique, the way that users coordinate sharing spectrum, does not take into account spatial dimensions. And as I mentioned before, it's a very crude mechanism. So if we really want to exploit the power of beamforming and interference reduction through MIMO in Wi-Fi, we need to change the MAC layer, either through standards, although that's a very slow process, and then you have to worry about backwards compatibility, which is part of the reason why the MAC protocol hasn't changed and is backward compatible all the way to 802.11b, or do something like I described before, having some software in the cloud that's managing the Wi-Fi access points. That's really the only way. Right now, Wi-Fi does a great job of exploiting multiple antennas point to point at the physical layer. It's tremendously powerful. It's at the Phantom limit almost. But in terms of taking antennas and using them with multiple users, it's not using it at all in Wi-Fi. And I just wanted to make one comment about the earlier discussion on dense networks. You know, dense networks aren't just cellular dense networks. It's not just having small cells. And in fact, part of the reason why there's been a slowdown in the exuberance around small cells is because Wi-Fi has taken over a lot of the burden that we anticipated would be on the cellular networks with the growth of traffic. Most people are offloading to Wi-Fi, or carriers are offloading to Wi-Fi, which is essentially a small cell. It's just a different technology. So I think when you say, will there be, you know, a wireless device on every light pole, I think that's very likely, but it may not just be an LTE device. It may be LTE, it may be Wi-Fi, it may be millimeter wave, it may be all three of those put into a single box. And I think it will evolve organically, where you will put much more dense concentration of wireless devices where you need them the most, where the capacity constraints are the highest. And then eventually, as the capacity demand grows, you will roll out denser and denser networks. So it's not like overnight, tomorrow you're going to see a Wi-Fi access point or a cellular base station on every light pole, but you will start to see them proliferate, and we already have seen that in places where there's, basically the networks are at capacity, and then it will evolve slowly. But it's not just going to be cellular. It's going to be a mix of these different technologies and new technologies that we can't even envision today. I think millimeter wave, what role that has to play remains to be seen. It will play a role. And there may be other wireless networks, including cognitive networks on the horizon, which will also play a role in this dense network of wireless devices.
Cognitive networks are important. How Wi-Fi plays in is important. We're also going to get to Henry's comment that is much spoken of in the industry, that he expects Moore's law to significantly slow down in the future. So let me stop a minute to introduce the organization sponsoring this event. The Marconi Society gives out the annual Marconi Prize. It's the most prestigious prize in communications. Henry Samueli, who's on screen, Paulraj, who is also here, AJ Paulraj, is this year's winner. All kinds of people who created these networks, from Tim Berners-Lee, who created the web, to Vince Cerf and Bob Hahn, who did, well, a whole lot of the early protocols of the web, and a whole lot since, have won the Marconi Prize. They're also proud of the Young Scholar Awards. The Young Scholar Awards go to people who, under the age of 27, have achieved something significant. And the age 27 was chosen because that's when Mr. Marconi, just over 100 years ago, did some of his crucial experiments. A lot of this is a young man's game, and I hope will be more of a young woman's game in the future. We know how few there are there. Let me take this over to a slightly different topic, because it's one that a lot of people want to hear. Henry, why do you think Moore's law is going to slow down?
Well, it's really a matter of physics. It's becoming exponentially more difficult to shrink the sizes of transistors. We're already, in the 14 and 10 nanometer realm of geometries on devices, and you have to realize that a silicon atom diameter is around 0.5 nanometer. So there's just not a lot of room for shrinkage. And most people are predicting that in the next 10 to 15 years, we will probably reach a limit as to how small we can make transistors on chips. And therefore, we'll reach a limit as to how dense these integrated circuits will become. So it will impact everything, because you can't just automatically extrapolate for the next 50 years and assume that you're going to be doubling every 2 years anymore. We've got about 10 to 15 years left of shrinkage to go.
When shrinkage becomes much more difficult, are there other technologies that will improve chip performance that will pick up most of the slack? Or do you think that's the challenge of bridge too far?
It's not, nobody yet has found an alternative technology that is going to replace our traditional silicon transistor technology that we know of today that will continue the Moore's law shrinkage. There are alternate technologies that will help. 3D technologies. Right now a chip is essentially a 2D device, but people have looked at stacking up the transistors in the vertical dimension to create 3D packages and chips. So that may help and ease the slowdown. But as far as a true replacement for CMOS transistors as we know them today, no one has yet identified anything.
One of the question just came in on LTE in unlicensed bands. Again, let me plug Marconi. Erwin Jacobs of Qualcomm, who has been the folks proposing this, is also a Marconi fellow. It's an incredible group of people to be able to work with, and I'm very glad of it. I'm going to take that over to Andrea, because you've been working on cognitive radio that can work in many different bands. Can you explain what cognitive radio fits in, and in particular, answer this question on how Wi-Fi and LTE might or might not coexist particularly in the high spectrum around 4.9, that there's a lot of spectrum being used for Wi-Fi. Andrea, you're the right person for this, aren't you?
Sure, and I think I finally figured out how to enable video. If you want to try switching to my video, I may actually appear on the screen. Does that work?
On what I have to
so I think that, so cognitive radio kind of began with the notion of white space and trying to find spectral opportunities under the premise that in the licensed band, spectrum was not used efficiently. And hello everyone. And in fact, I think that the cellular operators do use spectrum extremely efficiently, much more efficiently than in the Wi-Fi bands. So the notion of white space, I'm not a big believer in it, but I think that there's other cognitive radio techniques that have the potential to basically make more efficient use of spectrum across the board. There was ultra-wideband technology, which had a lot of challenges and wasn't very capable, and I think that's why it didn't succeed. But using multiple antennas, kind of along the lines of what Paul described, if you can figure out how to avoid interfering with primary users by pointing in a different direction with many antennas, I think there's a lot of promise there for using cognitive radios in the spatial domain to make more efficient use of spectrum. And then there's also work that has come out of my research and other people's on overlay cognitive radios, which is still, I would say, in the Shannon theory domain. We haven't figured out how to do things practically, but they're basically ways to superimpose cognitive radios on top of an existing network so that they actually help the existing network. You can think of that as a relay or other more sophisticated techniques, while also getting clean spectrum on their own. So I think that, in my view, cognitive radio is still pretty much in its infancy. It's still in the research lab in terms of the potential practical gains that we can get, but I think there's a lot of gains to be had there. And then just switching over to the topic of LTE in the Wi-Fi bands, you know, the problem in the Wi-Fi bands is really coexistence. That's a problem for Wi-Fi devices themselves. But now if you're going to put a whole other different system in the Wi-Fi bands, it has the potential to completely crowd out the Wi-Fi users. And I don't think that would be a good thing. I think the success of Wi-Fi has really driven the wireless industry, along with the success of cellular. And so I personally hesitate with the notion of LTE in the Wi-Fi bands. I think it would be better to continue to have the Wi-Fi band, the devices operating in the Wi-Fi bands, ensure that they can coexist so that they don't have one particular type of devices like an LTE device dominating the occupancy of the band.
And I believe we're going to invite Erwin Jacobs of Qualcomm, also a fellow of the Marconi Society, who has a different opinion on that subject. And when we have him, we'll invite the folks here who are asking those questions there. The question came in on quantum computing, and I think we're going to pass on that one because that's just stretching a little bit too far. You're seeing Professor ANDREA GOLDSMITH at Stanford. Also here are AJ Paulraj at Stanford, MIMO and other accomplishments, Henry Samueli of Broadcom, DSL, cable modem, Wi-Fi, and just about everything else in this business. Broadcom's achievements are remarkable. Okay, I'm going to ask us to go back to the question we opened, because I spend a lot of time with the folks in Washington on policy, and they believe that a spectrum shortage is going to be a crucial issue going forward. Now, that requires looking at demand, which isn't a problem for the engineers here, but the engineers here can tell us about capacity. So, Andrea, you're on screen. In the next 5 to 10 years, what kind of capacity increase do you expect?
The capacity increase within the existing spectrum, without new spectrum, I believe is primarily going to be driven by going to smaller cells and denser networks, and some gains on the physical layer. So, you know, more antennas, although we're limited in the next 5 to 10 years in terms of commercial developments, we're limited on, you know, maybe we'll see 2 to 3x there, maybe 2 to 3x using multi-user MIMO techniques. But primarily, and the question came up earlier about spectral efficiency, which is usually thought of as bits per second per hertz, but there's also an area dimension of that. You can think of it as bits per second per hertz per unit area. And the smaller you shrink the cells, the more that spectral efficiency goes up, even if you don't change anything about the physical layer. So I think that we can see in the next 5 to 10 years easily 10x improvement just based on physical layer improvements in denser networks, maybe even up to 100x. Getting to 1,000, I think, will require other breakthroughs in other technologies, as well as new spectrum. So I think that the spectrum that's being discussed in the 3 to 7 gigahertz range is going to be very important, can be utilized today with technology today and the MIMO techniques we have today to really increase capacity. And every hertz that you add in available spectrum adds that much capacity to the network. I also think that the higher frequencies of 28 and 60 gigahertz, I don't think we quite have the technology today to exploit that in the way that that is possible. But I would say if I look over, 10 years from now, we will start to see a lot of technology deployment in those bands, and that can provide a huge amount of spectral gains because there's just so much spectrum up there. And it's also unregulated, which makes it easier for innovation and startups to exploit those bands and build systems.
I'm going to bring Paul on. Paul, do you agree with Andrea on this?
I would agree with Andrea in all her comments. Certainly, the way we drive capacity is smaller cells, more spectrum. Both of these, of course, have their pushback. Small cells are difficult to do because of the fact will be done, but the pushback there is getting backhaul. You've got to connect them back to the network, and that gets expensive. Getting more spectrum, well, Wi-Fi is in a good position, about 600 megahertz, the 5 gigahertz band is a big answer. But LT, I think, in licensed band, FCC has been struggling to find more spectrum. It's been very slow. So I actually think that a dimension that we all know about and we're discussing in this call is antennas, is a very important dimension. And just think of it. Every time you add an antenna, you really are sort of creating an entire new swath of the same spectrum you have. So it's a wonderful leverage. And how it plays out, it turns out antennas at the clients is hard to add because of a variety of constraints, power, area, and so on and so forth. But antennas at the cell side or AP are somewhat easier. And in multi-user MIMO, you're adding antennas at AP is good enough. You can increase capacity. So I think antennas is already being explored and exploited to become even more important. And I would like to sort of go back to Marconi. He had many years, I think 100 years ago, it said that it's dangerous to underestimate the power of wireless. I would say he was alive today, he would be surprised how far wireless has gone. But he would probably add saying that it's even more dangerous to underestimate the power of MIMO wireless. Antennas have got a long way to go. We're at the very beginning of a major growth plan.
Henry, can I pin you down on this, or is it one you don't want to speculate on?
No, I think Andrea and Paulraj covered it very well, and they're obviously very knowledgeable, and I agree pretty much fully with everything they've said. So I look forward to these advances in MIMO technology to increase capacity.
Something remarkable has happened during this webinar. The attendee numbers have actually gone up throughout, and nearly nobody signed off. That is something when I speak, I really watch. Is the audience paying attention? And I want to thank our speakers for being interesting enough that nobody wanted to leave from the room here on the webinar. Let me go to each of you and ask you, Henry, you're on the screen now, what's the most important changes you personally will be involved in the next 10 years? What are you working on that will make a difference?
Well, I think it's enabling communications everywhere in the network. We focus very much on wireless today, and in particular, a lot of discussion on cellular and Wi-Fi, but communications is a much broader field. You have lots of wired communications. In fact, wired is a very preferred offload of backbone technology. When you offload cellular to Wi-Fi, it ultimately goes through your broadband connection in the home into the network. So expanding broadband access to the home is a critical piece of enabling a broader network capacity, enabling next generation infrastructure networks that can switch and route and transport, the terabits and petabits of data that are being generated. So it's a very broad problem that we're looking to solve here, and that's certainly our focus here at Broadcom, is to deal with not only the wireless aspects, but the wired aspects of the network as well, so that end-to-end, no matter what medium you're over, whether it's optical, copper, wireless, you have a high quality of service and high bandwidth.
Okay. Andrea, ladies should come before fall.
Okay,
what
thanks.
your own work is going to be first?
So, like Paulraj, I wear two hats, one in the university and one in a startup. So I see my own involvement in technology evolution over the next 10 years in both of those lights. So on the academic side, much of my work throughout my career has been on looking at fundamental limits of wireless technology and trying to find how the insights from those fundamental limits can translate to technology. So very early in my research, I was looking at adaptive techniques when everything was just trying to support voice at a fixed rate. And I think that, it took several decades, or at least a decade, for that to make its way into technology, but it did happen. Similarly with other OFDM is another example of the technology that Shannon predicted was the right way to use wide bandwidth, but it took some time to become commercially viable. So I think in the university, I anticipate continuing to look at fundamental capacity limits of wireless networks, cognitive radio networks, heterogeneous networks with different size cells, to try to find out, what is the optimal technology to best exploit the spectrum, independent of what's possible today in technology, so that eventually we can have networks that are really close to the Shannon limit. We're very far from that today. I hear in talks that I go to, people in industry saying, well, we're at the Shannon limit of wireless. We're definitely not. We're close to the Shannon limit of point-to-point wireless for a given number of antennas. But, we can add antennas, we can look at the network as a whole, and we're very, very far from what's possible from a fundamental perspective. Another area that I'm actually looking at in research is, how do we bring hardware constraints into our study of fundamental limits? So some recent work I've done is looking at what's Shannon capacity when you sample signals well below the Nyquist rate, because we don't have A to D converters that can sample fast with low power given the wideband channels that we're looking at. So I think bringing in hardware constraints into the study of what we do in the university, while still, pursuing fundamental limits, I think has a lot of potential to inform technology development. I also do a lot of work on massive MIMO. I think it's an area that as millimeter wave becomes more prevalent, there's a need for that. And what massive means depends on the spectrum that you're operating in. So again, at the lower frequencies, if you have 10 by 10 or 20 by 20 antenna arrays, which might be possible depending on space limitations, there's still a lot of technical challenges to solve there that we haven't even addressed in research, let alone in development. And then just putting on my other hat, which is my Accelera hat, I'm a huge believer in this notion of software-defined wireless networks. I think a lot of the issues that have been discussed on this call, how do we manage interference in Wi-Fi networks, in devices that are sharing networks, that's going to become even more of a problem in the Internet of Things, as you have billions of devices whenever the Internet of Things happens. And so I think being able to have a broader view of the network and across networks, across Wi-Fi, cellular, other networks, I think is very exciting, and it's a place where there's a need for the technology today, and that need will just continue to grow.
I brought on screen AJ Paulraj, Stanford professor, inventor of MIMO, this year's winner of the Marconi Award. The Marconi Society honors the people with great achievements in communication. What we're trying to do in these webinars is to bring the knowledge of these experts into the public domain. I, as a reporter, have had the pleasure of meeting many brilliant people and getting to talk to them. And there's a huge disconnect between what I hear from the best engineers in the world and what I hear in the general discussion. So I'm very glad that we're bringing folks more visible and that we're going to get this out. We will have the transcript. That'll take a while, and a recording of this will be up tomorrow. So let me hand over to this year's Marconi Prize winner, Stanford Professor AJ Paulraj, the inventor of MIMO and much else. What in your work is going to make a difference in the next 5 and 10 years?
I think for me, it's back to the future in the sense that I'm going to go back to look at, I'm a great believer in antennas and multiple antennas and how they can be used in different ways to improve performance of wireless systems. And I think the world has pursued some path, the single-user MIMO, multi-user MIMO, kind of distributed MIMO ideas. So I want to look at that even more closely. And so my goal for the next 5 to 10 years is to look at do out-of-the-box thinking on antennas and to try and build ideas which will further address the coming needs in wireless systems. So I'm going to sort of go back and look at antennas in a more fundamental way. And there are some very interesting ideas which you can bring in some totally new ideas into the whole space. I would also add, I've been very surprised, partly I think thanks to Broadcom, of how well Wi-Fi is done. I think nobody expected Wi-Fi to do so well, unlicensed spectrum and some other facts around it. So I think the world will sort of will discover unlicensed spectrum bands and Wi-Fi is really a huge opportunity for connectivity, and it's something that I'm begun to look at, and I do believe that there's a good combination of antennas and Wi-Fi which can do even more interesting things.
And with that, I want to thank everybody for attending this Marconi Society webinar. If you send us questions after the event, I'll be happy to pass them on. We will have a recording up, hopefully by tomorrow. We will have a transcript a little bit later. Thank you all. And as they say, good night.
Thank you.
Thanks, everyone. Thanks for your attention.
Thanks. Signing off. Bye-bye.
Thank you.